Hello, good morning students. So today we will begin with our second module. Here we will be focusing on the concept of torque. Okay, what is torque, how it is defined, how it is calculated, the specific formula used to find out torque acting on a body, and we will also see how torque and angular momentum are related. Previous class we talked in detail about angular momentum. Okay, and we will see some physical applications on a certain mechanical system, how torque is calculated. Okay, so these are the essential points that we will be discussing in this module. Okay, so first, what is exactly torque? So, okay, this is an interesting question, intriguing question. What is meant by torque? It's in fact a Latin word actually, torquere. Okay, so its simple meaning is to twist something. Okay, you know what is twisting? So some sort of turning, you can say, turning effect. In fact. So technically or officially, this word was introduced by James Thomson. Okay, he is the brother of Lord Kelvin. He introduced this word in engineering in 1884. So, okay, officially this was how the word torque got introduced in physics. And today we know it is in fact the rotating effect of a force. So, okay, we have the force, we have the torque. Both are not identically same. Force, in fact, if a force alone is acting on a body, it can produce some sort of linear motion. But if a body is experiencing a torque, qualitatively you can say, that can produce a turning effect or a rotating effect on a body. Okay, so any force that can produce a rotating effect, that we can call a torque. So it means that all forces are not torque. Okay, all forces are not torque. Certain forces can produce a torque. Of course, okay, that and all torques are actually some force involved. So vice versa relation is not true here. That means all forces are not producing torque, but all torques there is some underlying force. You can say like that, and you can express mathematically torque as the cross product, a vector cross product of position vector and force. So what is position vector? What is force here? Suppose you are applying a force at some point on a body. So with reference to some point O, force is like this. Okay, so you have a vector R, position vector. That vector points from the point where it is acting, and there is 2 points. One is the point of acting, and one is point at which the force is acting on it. So a reference point like that. So that is what is shown with the position vector, and the vector of is the force. And there is of course an angle, an acute angle between force and R. That acute angle is always taken in finding this torque. Okay, so R cross F you can expand, so you will get the magnitude of R, magnitude of F, and sine of the acute angle between R and F. How this is coming, we will be shortly understand it. Okay, so we can say torque is analogous quantity of force in rotational motion. And in fact, they are not same, and even their units are not same. But in SI system, the unit of torque is meter. Because of the obvious reason, it is evident from the formula. R is measured in meter, and the force is measured in Newton. So we write in Newton. Okay. There are so many situations in our day-to-day life where we come across torque. For example, a nut ball system, when you tighten it or unscrew it, you use a wrench or a spanner. where definitely there is the role of torque, and whenever you are using a screwdriver to remove a screw, again the role of torque plays an important role. Similarly, nut bolt, you must have seen a railway track, how they tighten the railway track, girders and all. Another situation comes in the removal of a car tire, where how tightening car is properly, the tire is properly bolted with the car body. So that these are different physical situations where we can see the role of torque in our daily life. Okay, so now we come across how can we write? Why do we write torque as R into F into sine theta? The reason we have to analyze. For that, consider the first figure. Here, this O is the point, reference point with reference to which the force is acting, and the force is acting at a distance R. Okay, at a point P. Then force is at some arbitrary angle, and you can see vector R and F are not exactly perpendicular. In such cases, what we take is, we take the perpendicular component of R with reference to force. From the figure you can see that, the vector R you can resolve along two mutually perpendicular directions. R cos 90 minus theta and R cos theta. You get a 2 angle. This is theta. So R cos theta is this one, and R cos 90 minus theta is this one. And you can see R cos 90 minus theta is exactly perpendicular to force. So you can write force into perpendicular component of R. Okay, component of R perpendicular to F. So you torque you can now write torque is equal to force into R cos 90 minus theta. So that will give you F into R sin theta. So this is one way of interpreting what is the torque acting with reference to the point O. Or in other words, you can take component of force also. We have the position vector R. Now take component of force perpendicular to R. Component of force, previous one, component of R perpendicular to F. That was R cos 90 minus theta. In the figure, in the second figure, you can write R multiplied by component of force perpendicular to R. That is also true. Okay, in this case, we can write component of force perpendicular R into R. Okay, so that again gives you Fr sin theta. Okay, this is how physically we can interpret the relation torque is equal to F into R sin theta. Okay, this is the reason. So mathematically you can write it as R F perpendicular or R perpendicular F. So here F perpendicular means component of F perpendicular to R. Here component of R perpendicular to F. So that we in fact we write R sin theta or R F sin theta. Okay. So in a vector form, you can definitely write vector R cross F. And here one more thing we have to take into account, that is the direction of the torque. Direction of the torque will be always perpendicular to both R and F. This is obviously calculated from the right hand screw rule. Okay, for which you bring R and F such that the tail end of the head and tail, okay, the head end of the force and R are kept together, and you rotate from R to F. When you rotate from R to F, that is a clockwise rotation. Okay, clockwise rotation. So you can see that a right hand screw will move downward. So in this case, using a wrench, you are rotating a nut. So the nut will move downward, not the bolt. Okay. So that is how. Okay. So direction will be downward. So in this way, the direction of torque at any point you can find out, provided that vector R and vector F is clearly given. Okay. Just to follow the a rotation direction of a right hand screw. Okay, that will give you the direction of torque. And magnitude is simply found as magnitude R, magnitude F, and sine of the angle between R and F. The angle should be the acute angle, the smaller angle between R and F. So I hope the physical sense, its mathematical implications, and the geometrical ideas are clear. Okay, now again, when you come to a 3D space, how can we represent torque? In a 2D space, it is very simple to understand. When you come to 3D space, you have vector R, you have the vector F. Of course, you can write in a determinant form, ijk, xyz for position vector, and fx, fy, fz for the force vector, its component along the xyz direction. Then, as you normally expand the determinant, you get this kind of a form. And here we have the x component of torque, you have the y component of torque, and you have the z component of torque. And you can briefly or compactly write as I cap tau x plus j cap tau y plus k cap tau z. Here the tau x, tau y, and the tau z component will be given by this expression. So this is the most general form of torque. Okay, how it is expressed in a three-dimensional Cartesian coordinate system, or even you can express in any other spherical or cylindrical coordinate system. You can express torque. I hope this idea is also clear. You can do any sort of problem using this general form of torque. Okay. And now again come back to what is the difference between torque and force. There are many differences. Even though torque is produced by force, still torque, first thing is that torque depends on the origin and the distance between the point of action and the origin. Okay, that's the first thing. That means the distance factor is always involved. For example, in this netball system, we are using a spanner to tighten it. So this length is very important. How far away point you are acting, you are applying the force is very important. So distance factor is important in torque, whereas in force, distance factor is not important. For example, when you are moving a block in a unilateral direction, there is no question of distance, only force acting on the body needs to be known. And another important thing is that torque and force are always mutually perpendicular. It's a very interesting idea. Okay, you know, torque is equal to R cross F. So if R and F are in a two-dimensional XY plane, then torque will be in the Z direction. Okay, that shows that torque is perpendicular to force. This is always true. Whatever be the direction of force, torque direction should be always perpendicular to force. And there can be torque on a system with a zero net force, and there can be force on a system with a zero net torque. Okay, these kind of situations we come across in different cases. Okay, for example, when a seesaw is in equilibrium, or in a ballistic galvanometer, it is in equilibrium, there is torque acting on it, but still it is in equilibrium, and net force is zero. And similarly, force on a system can be, there can be force on a system. Suppose a body is moving in a linear path, there is force on it, but since it is not having any rotational effect, we can say no torque is acting on it. That can also come out. Okay, so that depends on the situations, and there are different situations in our day-to-day life where torque is used. For example, when you open a door, you can open the door by pushing at any point along the plane of the door. But the maximum torque the door will get when you hold at this point, at the edge of the door. Okay. Or at all other point you will be applying less torque, hence you have to apply more force to open the door. Whereas when you apply the force at the edge, this edge, you have to apply the least force, because the distance between the point of action and the force is large at the edge. That is the reason. Okay, in case of a bicycle, force on the pedals produces a rotating effect. That is a very well-known idea to you. And the cap of a bottle is opened by torque. You have to apply sufficient torque to open the cap of a bottle. A screw can be removed or unscrewed by torque. For loosening and tightening nut and bolt, you have to apply torque. That's common examples. And now come the term static torque and dynamic torque. One is static, that means torque is constant. And the second case, torque is dynamic, that means torque is varying. When you open a door, what you are applying is a static torque. Okay, when the door is open, you are not accelerating the door. You simply move the door by some constant angular velocity, you can say. Or when a fan is rotating with a constant angular velocity, we can say it experiences a constantly static torque. Understand? These are simple examples. Or when you are moving a bicycle with a constant velocity, that is an example for a static torque. But if you take the case example of a sports car, a racing car, the moment you start from the starting point, it speeds up to enormous value. In that case, in fact, the velocity, the angular velocity as well as the torque is increasing with respect to time. So, torque become a time dependent factor. Or you can say torque is dynamic, that means it changes at every time instant. Okay, so this way static torque can give you constant angular velocity, whereas a dynamic torque can give you a constant angular acceleration. So that is how we can distinguish between static torque and dynamic torque. Okay. And now come to a very important point. We want to relate the angular momentum and torque. Previous class we talked about angular momentum, and now we have the torque. These are two important parameters in rotational motion. And we know angular momentum in the previous class we studied vector L equals R cross. Okay. So here now you differentiate both sides with respect to time. You differentiate with respect to time both sides. You can write like this. Okay, R delta L by delta T, partial differential of L with respect to time. So both sides you have to take that the partial differential. Of course, when you do the differential, you have two functions here, two variables here, R and P. You have to differentiate both. So we have delta R by delta T cross vector P plus vector R cross delta P by delta T. Okay, delta R by delta it is nothing but the velocity, and delta B by delta T, rate of change of momentum is force. So we can replace this one with velocity and this one with force. Okay, so we have this relation delta L by delta T equals V cross P plus R cross F. I think this idea is very clear. And again, you have the vector P, which is nothing but momentum. So you can write mass into velocity. And here you can see we have two vector quantity, vector V here and vector V here. And whenever you take the cross product of a vector by itself, obviously it should be 0. Okay, obviously the V cross V should be 0. So what we get? This will become 0, and remaining what is left is R cross F. So we have delta L by delta T equals R cross vector F. Okay, R cross vector F is nothing but the torque acting on the body, and we have studied it. So we can say the torque or torque is equal to time rate of change of angular momentum. Okay, this is something connected with our linear motion. In linear motion, we had vector F equals delta P by delta T. Delta Yes, delta P by delta T. Force is equal to rate of change of momentum. So you can see tau is equal to delta L by delta T is the rotational equivalent of Newton's second law. Okay, time rate of change of angular momentum of the body equals to the torque at T1h. So it's a rotational, you can say second law of Newton's second law of motion. In rotational motion, rotational domain, you can write like this. So it's called equation of rotational motion. It's a very important relation which will be very frequently using in our subsequent discussions. Understand? So many physical situations, mechanical motions, rotation motion, we will describe using this, and we can find out many parameters or understand many mechanical systems using this equation. Okay. In relation to the previous equation, we have a law that is called conservation law of angular momentum. Okay, it is like this. If tau is equal to 0, okay, if the applied torque, external torque on a body equal to 0, then what happens? Delta L by delta T becomes 0. Partial differential of angular momentum becomes 0. That implies what? L should be 0 or it should be constant. Okay, so L is equal to 0 is a trivial case. Okay, we are discussing only rotating body. We are not discussing about a body which is absolute rest. We are discussing on bodies which are in rotational motion. Then there is no question of L is equal to 0. Only we will be dealing with the L is equal to constant. So what does it mean? L become a constant. Or in other words, if the external torque acting on a rotating system is 0, then the angular momentum of the system is conserved. That is the final result. Okay. If no external torque is acting on a body, then its angular momentum remaining constant or conserved. A similar law exists in linear motion also. If the external force acting on a moving system is 0, then linear momentum of the body is conserved. Okay, such a principle or law you have studied in linear motion. Suppose you take the case of a train. We are talking about a almost ideal case. A train, suppose it is moving with a constant velocity on a straight railway track. Assume that the track is very smooth. Suppose engine is suddenly switched off. You can see that train will move on with the constant velocity. Okay, I am approximating the situation. You cannot say ideally it is a good example, but just for your understanding, I am saying that that is an example of a linear motion, conservation law. You can apply roughly to a train moving on a horizontal, level, smooth railway track. If the engine is suddenly switched off, the train will move with a constant velocity. Okay, a rough example. Similar example you can talk even in rotational motion. Okay, that we will be doing very shortly. And this law, principle of this law, that external torque is 0, then angular momentum is constant, is actually called the principle of conservation of angular momentum. Okay, and let us see a good example for this principle of conservation of angular momentum. Just like that, we discussed the train example for principle of conservation of linear momentum. This is also a rough example, not an ideal example. In fact, take the case of a spinning motion of Earth. As a very spinning motion of Earth is a case where we can apply principle of conservation of angular momentum. Since the Earth is rotating with the constant angular momentum, virtually constant angular momentum, and no torque is applied on it. Okay, as you know, nobody is there to apply a torque, an external torque on Earth. You know, nobody is there. So torque is 0. So what happens? Angular momentum is constant. So that means the Earth is rotating with the constant angular velocity. But you must understand that there is a slight change. Scientists have understood, explored this fact, because Earth's shape is changing. Tall buildings are coming. Okay, huge buildings are coming, and Earth mass is getting displaced from one place to another place. So, because of various other factors, the angular, I can say, the moment of inertia of the Earth is changing. So, there is some slight change in the angular momentum. In fact, that is there. And keeping aside that, you can, for the time being, you can take angular velocity of the Earth is constant, because Earth is not experiencing any external torque. And when you discuss angular momentum, both magnitude and direction is important. And you know, Earth is rotating with reference to an axis that is pointing. The axis is pointing towards pole star. Okay, so it is inclined at an angle of 23.5 degrees. So, and direction is also constant. That shows that direction is also constant. So, both magnitude is constant, direction is constant. So, this way you can elucidate the idea of angular momentum on spinning Earth. Understand? Spinning Earth is an example. And similarly, even you know, Earth is revolving around the Sun. Okay, this animation shows that Earth is revolving around the Sun, and during this motion also, it's a revolution. You can say it's a revolution. The first one is a rotation. In this revolution also, its angular momentum is conserved every point. Okay, every point. First thing, it is revolving in a plane, and secondly, it's a product of mass and distance. Okay, distance between the center of the Sun and Earth is varying. This product is always constant. So you can apply the conservation principle on both rotational motion as well as the revolutionary motion around the Sun. Okay, so I hope the idea is clear. So constancy of magnitude of rotation leads to almost equal day and night. Okay, and the constancy of direction gives you different seasons. Okay, that's why, because Earth is inclined at an angle of 23.5 degrees. That is why we have different season around the around in a year we get a different season. The basic reason for that is that Earth is inclined at a particular angle. I'm not going to the details. You may get the details from any geographic textbook. So that's left for you. And now the relation between angular momentum and omega, angular velocity. Omega is angular velocity. So you have already L is equal to R cross P, and you know, if R and P are mutually perpendicular, okay, R is like this radially and P is like this. This is the case of perpendicular. So then angular momentum L can be written as RP sine 90. Sine 90 is 1. So we simply get R into P. Okay, we are talking only about the magnitude, and P is mass into velocity. So we have a combination. And you know, velocity in a rotational domain, velocity can be written as R omega, because omega is angular velocity. So you can replace your velocity with R omega. So we have L equals R into M into R into omega. Okay, so R can be multiplied. You have the MR square. So L equals MR square omega. So you get an important relation. So you see, now we related angular velocity with the angular momentum. Okay, and this equation is very relevant in many cases. You can apply this newly developed equation in the conservation of angular momentum. So consider a man sitting on a rotating chair. Okay, rotating chair. Suppose no external torque is acting on it. Okay, no external torque is acting on it. Or is sitting on a smoothly rotating, frictionless rotating table. So no external torque means its angular momentum is constant. Okay, so you can write M angular momentum L is equal to R MR square omega. And now you see that in the figure he is extending his hand. On both hands he has hold some bottles, and he is extending and bringing away and closing down the arms. So what happens? Yes, his arms distance increases from the axis of rotation. But angular momentum is constant always. So whenever he extend his arms, what happens? R1 will increase. So in order to make the L constant, omega should decrease. And similarly, whenever he brings closer the arms, his R1 will decrease. Then automatically his omega 1 by omega will increase. Okay, so that angular momentum L is always kept constant. So if you take two such configuration, one closer arms and one extended arms. In these two situations, we can write in closer arm situation, we can write L1 equal mass R1 square omega 1, and extended arms case, you can write L2 equals mass R2 square omega 2. So always torque is 0 and L is constant, and you can equate both relation, and mass is always constant. Okay, total mass is always a constant. So by cancelling mass from both sides, you get a very important relation. R1 square omega 1 equal R2 square omega 2. That means in the case of a man rotating with a constant angular momentum on a rotating chair, the product of this R1, R and omega should be always constant. Okay. So that's a very good example. You can see even in a fan blade. Suppose a fan is rotating with constant angular momentum. Suppose you hang up some towel or some heavy body on the leaves of the fan. You can see that suddenly the speed of the fan will come down. Okay, and whenever you take it out, the hanging clothes or heavy body, suddenly the speed of the fan will rotate. The angular speed of the fan will increase. Similar situation you can see anywhere. Suppose you take the case of a concrete mixer. The moment the concrete mixing material is placed inside the chamber, the angular speed will decrease. The moment the concrete mix is taken out, it starts rotating with increasing angular velocity. So these are a different situation where you can apply the conservation of angular momentum physics. Okay. So hope you have seen how the principal laws are applied in our day-to-day life situation. This way you can relate any such a physical theory, physical law to many life-related application. This is one way to understand physics in a better way. Okay. Another situation is coming here. A dancer, ice dancer. The moment she is spinning up with some constant angular momentum, the moment she extends her hands, you can see that angular velocity comes down, and the moment she brings closer her arms, angular velocity will increase. Okay, this is a very beautiful video you must have seen in Olympics and many other such reputed sports event. Okay, so there is some physics involved in this beautiful rotation. Okay, so here is the first assignment. Question is like that. The angular momentum of a spinning top is given by the expression. Okay, you have a spinning top here. Its angular momentum is magnitude alone. Okay, it's a time dependent quantity given by A0 e raised to minus t by 2. So there is some time dependence. Where A0 is a constant, compute the torque acting on the top at the time instant t is equal to 0.04 seconds, where value of A0 is given 6.28. Okay, you can find it because we have the relation for torque. Okay, you differentiate it, you will get some expression, and you insert the value, you find the value of torque. Keep in mind, the torque must be expressed in SI units. Okay, you get the answer. You have to do the problem neatly and submit in the Google Classroom. Okay, answer is not given here, so you have to do the problem and submit your answer, submit your work in the Google Classroom. And you have another question here, again connected with the conservation of angular momentum principle. Here is a carbon monoxide molecule. carbon monoxide molecule can rotate like this. Okay, there is an end-to-end rotation like this. This is an angular velocity. It has some quantum mechanical connection. We are not going into it. Our problem is very simple. Okay, here is the problem. A carbon monoxide molecule of body length 1.13 angstrom is freely rotating with an angular velocity of 7.5 into 10 raised to 14 radian per second. So that is the angular velocity. Okay, what should be the bond length of carbon monoxide molecule when it rotates with half the angular velocity? Okay, so this problem has the basis from our last slide. We discussed about angular velocity and the radius relation between L and omega. You can make use of the relation and you do the problem with utmost enjoyment. Okay, do it with all entertainment and enjoyment. Don't do it as a tough task. Do it properly and get the correct answer. Again, this is the assignment number 2. Do it neatly in a A4 sheet and take a scan copy and upload in the Google Classroom. Okay, so these are the 2 tasks. So you watch the video at least twice before doing the problems and understand each and every concept neatly and do the problem. Okay, so with these remarks, let us conclude today's topic. Wish you all the best. Thank you.